We begin with a word of prayer. So, Heavenly Father, we thank you for this day. Thank you for these students, and I just pray you to be with us today. Help us to glorify you in what we do, Lord. In your name I pray. Amen. All right, so now that we have that unpleasantness behind us, let's go on. Today, we are talking about vector spaces. So up to this point, we haven't, if I was to be honest with you, really been studying linear algebra. Up to this point in the course, what we've really studied has been what you might call matrix theory. So matrix theory used to get a lot more airtime in high school, but since it's not on the AP test, and since we teach to the test rather than giving students an education, it tends to get shortchanged these days, which makes this course artificially harder than it actually is. But anyway, so up to now we've been talking about really the study of matrices and how they can be used to solve linear equations, right? This is very old. This is more or less the techniques we look at were known in China, a couple millennia ago. Linear equations are very old. Babylonians, all these ancient civilizations, because linear problems appear in lots of applications, right? But the formal concept of a vector space is relatively modern. The definition I'm about to write down probably dates from the late 19th century. Peano? It's one of the sort of formal mathematicians of the 19th century. It seems to be due to him, maybe. I don't know, these sorts of things are not exactly clear where exactly the definition was first written down. Tends to be a progression of thought which finally coalesces with somebody saying it somewhere authoritatively. So I'm not sure about the exact history, but this definition has been known for at least 100 years, more than that. And it really sets the stage for the rest of the course, all right, which is linear algebra. Linear algebra is the study of vector spaces and the transformations which are natural to those, namely linear transformations. So what is a vector space? Well, in a nutshell, it's just some set where you have a natural method to add and scalar multiply vectors. That's it, right? But we should be precise, so let me write this definition for you. Definition, a vector space V, all right, over a field F, all right, is a non-empty set paired with two functions. In particular, those functions are plus, right, which goes from the Cartesian product of the vector space to itself back to V, right? And also scalar multiplication, which I usually use a little dot for, and that goes from the field across the vector space back to the vector space again, all right? So I'm saying that those are functions. In particular, here's the way the map works. We take x comma y. It maps to x plus y. That's our notation for vector addition. And then, of course, a scalar comma x maps to our notation for the moment will be c dot x. But I will admit, later, we omit the dot and we just write cx. Later, we'll just use juxtaposition for scalar multiplication. But today, I want to prove a few things about scalar multiplication. So that dot's important. So we can distinguish that dot from multiplication in the field, which is just, we're going to, well, anyway, more on that in just a minute. And they have to satisfy these axioms. Axiom 1, x plus y is equal to y plus x. Axiom 2, x plus y plus z equals to x plus y plus z. You're like, you didn't say anything. Well, let me put the parentheses in. So I'm saying that the addition is what? Associative, right? These have names, which I'll write in a different color here in a minute. Axiom 3, there exists 0 in the vector space V such that 0 plus x is equal to x is equal to x plus 0. Right. And I should put some qualifiers here. This is for what? For all x and y and v, right? This one's what? For all x, y, z, and v? And this one is what? For all x and v? Axiom 4. For each x and v, all right, there exists something called minus x in v, such that what? X plus minus x equals to 0. And while it's not logically necessary for pedagogical reasons, let me just point out that that's also minus x plus x. In fact, disclaimer, the definition I'm writing right now is not logically minimal. I mean, to a proper, pure mathematician, perhaps of the French variety, this is an offensive definition because I am giving you more. Some of these statements are redundant. You can prove one from the other. So why do I give this slightly more lengthy definition, not logically minimal, is for pedagogical reasons, just because these are the things we want to think about when we think of vector space. It's something with all these things, right? But admittedly, it's not logically minimal. If you want to see a logically minimalistic definition of vector space, probably find a good French math book. Let's see here. 1 times x, one scalar multiplied by x, is equal to x for all x and v. And what's this 1 I'm speaking of? 1 is an element of the field, right? It's the multiplicative identity. It's the 1, the unity, multiplicative identity in the field. It's a number, though. All right. Axiom 6. You're like, is there any end to these axioms? I know, right? So if we have multiplication of AB in the field, scalar multiplying x, well, that's the same thing as scalar multiplying A times the scalar multiple of B times x. Notice the dots. 2 scalar multiplications here, 1 here. This is a multiplication in the field. All right? Let's see here. That is for all x in the vector space and for all A and B in the field. Axiom 7. If we have scalar multiple of A times the sum of 2 vectors, x and y, well, that's equal to A times x plus A times y. Again, scalar multiple. These are not dot products. The dot product would not be an example of a scalar multiplication, usually. Now this, of course, is for all A in the field and for all x and y in V. So most of these axioms are like for all statements, right? But there is an existence one stuck in here somewhere, which kind of cramps my style. So, I mean, I guess if you want to do less writing, we should like pick off, I don't know, but the flow here is I need this one existence axiom right here. So like I would love to write at the start, for all x, y, and z, these things are true. But see, when I get to this right here, it kind of cramps my style. But anyway, maybe you guys are smarter than me. You can figure out a way to do a lot less writing. Okay, so axiom 8. Let me say interesting things and stop jibber-jabbering. So your a plus b, scalar multiplied by x, is guess what? A times x plus b times x. And that, again, would be for all a, b in the field and for all x in the vector space. Oh, yeah. Axiom 9 and axiom 10, these are really redundant. This says for all x, y, and v, we have x plus y is an element of v. And the axiom 10 says if x is in v and C is in F, then, and I still didn't do it right, then C times X is a single element of V. In this axiom 9, I should have said it's a little bit more than this. It's not just that X plus Y is an element of V, it's that X plus Y is a single element of V. All right. Whew. Now that's a definition. So let's put some words in here, right? So this axiom 1 is what? Plus commutes, right? Addition is commutative. Axiom 2 is associativity of addition. What's axiom 3? Axiom 3 is existence of the additive identity. Existence of 0, right? AKA the additive identity. What's axiom 4? Axiom 4 is existence of additive inverses. If you wanted to explain it to your grandma, maybe you'd say axiom 4 makes certain that we can do this thing called subtraction, right? But nowhere is subtraction part of the definition here, is it? Not really. And then axioms 5 through axioms 8 do what? These all describe what? All of these axioms describe the interplay between vector addition and scalar multiplication, right? By the way, from a group theory perspective, if you just isolate axioms 1, 2, 3, and 4, paired together with the preamble here, this makes a vector space what's called an abelian group under addition. That is, of course, a forward-looking comment for those of you taking Math 421. It's also a nice way to summarize axioms 1 through 4. Now these, this basically says that the one scalar multiplies in the natural way. I don't have good names for these. These axioms 7 and 8 are distributive. Can someone say that word? Distributive properties. Yes. Now, can you guys tell me? I won't try to pick out all the redundancies, but can you tell me logically why axiom 9 and 10 are unnecessary given the preamble here? Like, what does it logically mean to write this? I'm saying that addition is a function, right? It's a function from v cross v to v. What's that say? It says for every pair x comma y, there is a uniquely assigned, a single element in v, right? So that's axiom 9. And to say that this is a function is to say that for every scalar and vector, I get a vector, right? So this is tantamount to axiom 10. Any questions about the definition? All right, good. So once you have this definition, you can start rattling off examples, and so that's what I'll do next. So what are some examples of vector spaces? Oh, by the way, a convenient notation for us is rather than writing this v over vector field f, is we can just write v of f to express that. Okay? Welcome. All right, so let's look at some examples of vector spaces. So what does it take to define a vector space? We need what? We need to choose a field. So let's set the field equal to the reals, right? And let's take the vector space to be equal to Rn. Okay? If we say, we're going to say x plus y, the ith component of that is equal to x sub I plus y sub I. And if we're going to say c times x, the ith component is equal to c times x sub I. And this, of course, is for all x and y in Rn and c and r, right? In other words, Rn with the standard vector addition and scalar multiplication, we know these things, right? Vector addition is commutative, associative. Scalar multiplication in Rn works like this. In fact, this whole definition is really modeled on that example, right? The point is trying to abstract that to come up with something that has the same logical core as this example, but is not this necessarily, right? So yes, this is in fact a vector space over the reals. And once you have that example, you want to be greedier. You can say, well, we could also look at Fn over F, right? In other words, look at, V equals to Fn, right? Again, with the usual vector addition and scalar multiplication, just like I wrote above, except replacing reals with the field F, it's still a vector space, right? So, just to unwrap that a little bit, we have, we could say Cn, right? Or we could say Z mod a prime to the n. These are natural vector space over the complexes. And this is a vector space over Z mod P, right? The finite field with P elements. Now here's where it starts to get weirder. I could do something a little bit in between. I could take V equal to the complex numbers, right? I could look V equal to the complex numbers, and I could look at it, consider as V over the reals. Right? What's a complex number look like? Z equals to A plus IB, right, is a complex number. And it's fairly clear that if you just use the usual addition, Z1 plus Z2 is going to be a complex number for all Z1 and Z2 in the complexes, right? I mean, clearly the sum of complex numbers is a complex number. And it's easy enough to check that the complex numbers are commutative, associative, right? But then how about real scalar multiplication? Does it permit real scalar multiplication? If I take, C as a real number, and if I take C times A plus IB, do I get a complex number again? Well, this gives me CA plus ICB, right, which is, again, an element of C. So yeah, scalar multiplication of a complex number by a real number still constitutes a scalar multiplication. So we can look at the complex number system in two different ways. We could look at it as a vector space over the complexes, or we could look at it as a vector space over the real numbers. Yeah. And in fact, there was really nothing special about using complex numbers here, right? I could have done something like this. Well, let me behave. I'll write it over here. Same thing with Cn, right? If we take V equal to Cn, the n tuples of complex numbers, then if you take a vector z, you can write it as x plus iy for some x and y in Rn, right? You can take the, for each, I should say it up here, for each z and Cn, right? If we look at n tuples of complex numbers, you can always take those, and you could break it into the real piece and the imaginary piece. You can add them together. If you look at that, you've got a sum of a real n vector plus another real n vector times I. Right? Any complex n vector has such a decomposition. And you can observe, if we take C a real number, right, then CZ equals to CX plus ICY, right? And that's again an element of Cn. So you can make Cn a vector space over the reals. So I hope you're seeing that if you just say, I'm going to consider the vector space Cn, that's ambiguous, right? I have to tell you, am I taking the field to be the complex numbers, or am I taking the field to be the real numbers? Right? But it gets weirder. I could also use the rationals, right? The rational numbers also form a field. And if you look at these comments I just made, we could just as well consider the real numbers, you know, we could consider Rn a vector space over the rational numbers. Right? Think about it. If you take an n vector, closed under addition, right? Take an n vector, multiply by a rational number. Here, I'll write it down. So let's take V equal to, say, Rn, and let's take the field to be the rational numbers. What happens if you take, you know, a rational number, say P over Q, right? I'm going to just use R for rational, and you multiply it by x1, x2, xn. What happens? Usual definition of multiplication, scalar multiplication, we just get what? Rx1, Rxn. Is that still a n tuple of real numbers? Is a rational number times a real number still a real number? Yes. Right. So in fact, yeah, still a vector space. Yet a different way of looking at the, you know, Rn as a vector space over the rational numbers. Okay. All right, enough of that. More examples. Let's look at kind of more interesting examples. I got to leave these axioms up here for a bit. We're at example 6. If you look at V equal to Rm by n, right? And you let A plus B ij equal to Aij plus Bij, and if you let C times A, the ijth component, to be C times Aij, right? For all A and B in Rn by n, and for C in, you know, R. So this is, you know, I'm taking it to be over the reals for the moment. Yeah, m by n real matrices over the real numbers form a vector space because the sum of matrices is a matrix. Its addition is associative, commutative. There's a zero matrix. Every matrix has an additive inverse. If you scale and multiply matrices by numbers, it satisfies all these good things, right? These things we know. So a matrix is a vector, is what I'm saying. Because we call the elements of a vector space vectors, whether or not they're the column vectors that you've grown to know and love. Or fear. I don't know. Hopefully not fear. Don't be like Yoda. So, and again, this example, we could easily take R and replace it with what? You could replace it with the rational numbers, right? And our n by n real matrices are also forming a vector space of rational numbers. But example 7, you could just as well take V equal to F m by n, right? Over F. That's also a vector space with respect to the natural addition and scalar multiplication of matrices with entries taken from a field F. Could be complexes, could be Z11, Z2, pick your prime. Make sense? But there's more. 8. Think about functions. from S to V, where V is vector space over a sim field F. So by this I mean the set of functions. So let me be more specific here. And let me, instead of saying V, let me call this W. So I'm going to say my vector space I'm introducing is this guy. The function space, so let me be more specific here. If F is an element of V, what's that mean? F is a function from S to W. What's S? It's just some set. I don't really care. Any set will do. I don't need any kind of linear structure there at all. Oh, by the way, in other cultures, vector spaces are sometimes called linear spaces, or sometimes linear manifolds. Yeah?
Just a quick question. In example 6, is it supposed to be all A and B elements of M by N?
Oh, yeah.
Okay.
Sorry. You're being a square, man. It's true. I'll try to keep it mellow. There we go. M by N. Yeah, that was not supposed to be square. I want to be a triangle. Oh, I'm sorry. I used to watch Simpsons. Then it's gotten so political lately. I don't know. I did enjoy the Yahoo comment I read recently. It was like, well, Trump was right about one thing. The Russians didn't medal. It's an Olympics joke. Sorry, it was kind of clever. Anyway, I'm just excited about that Trump film we're making. It's exciting. See here. So where are we? Okay. Sorry, I had to swallow a comment. So a function goes from S to W. That's the object. So the vector here I'm saying is a function, right? So if this is going to be a vector space, up till now, all of my examples, it was stupidly obvious how we should add them and scalar multiply them, right? It's still not that hard to figure out here, but how should we add functions like this? So suppose we have F and also G in V, right? And we'll pick C to be an element of the field, right? What we should like is that F plus G is also a function. So how do we define it? We say F plus G of X. So this is a little pre-calculus for you right here. F of X plus G of X, right? And the scalar multiple of F, C times F, is going to be C times F of X. And this, of course, is for all X in where? Right, in the common domain we insist on for all these functions, namely S. And you can, now why is this addition commutative? Why is it that F plus G is equal to G plus F? What does it take for two functions to be equal? They have to be equal on all their values, right? How is it that F of X plus G of X is equal to G of X plus F of X for all possible X? What gives me the right to make that claim? What did I say? I said W is a vector space over F, right? So that means that F of X plus G of X is equal to G of X plus F of X, because this is happening where? In the target space of F, right? In its values, in W. Because the image of the function happens to take place in the vector space, that means we get the addition commutes, right? And it's associative. So and what I'm trying to say is the commuting and the association property, the scalar multiplication properties, the distributive stuff, all of that transfers over from W to the function space. Maybe there's one thing that's not immediate. What should 0 be in the function space? How can we? You need zero function, so I call it zero fun. Zero fun. You're like, yeah, it's how I feel about this place. See, zero fun. So zero fun of x. What should the definition of that be? You like this class? I know. I said it first, so you can't say it. Ha. Zero fun of x equals what? Define the zero function for me. Zero? Wrong. No. No, you're right. You're right. Sorry. You guys have some confidence in yourself, you know? Come on. But yes. So there you go. There's the zero function. Oh, how about the additive inverse? Let's be negative. Minus f of x, by definition, should be what? Yeah, f of x minus, right? Where that minus is coming to us because we've assumed W is a vector space. So the inverse exists, additive inverse exists.
Underlined or is that congruent?
What?
Right there.
What said you?
With your additive inverse.
Oh no, yeah, my default, long-standing default is when I write equals equals equals, as I call it. That means definition.
Okay.
But you're right. Some people use equals equals equal as a as an identity, right? Some people use it as congruence. So, oh, you're fine. I want picky. Picky's good. Not picky is why I own so many points now after grading your test. And so I have more than I'd like to have, honestly. But yeah. All right, so those are our basic examples. All right. At this point, you should be like, so I have to prove something's a vector space. That means that I have to show all of these axioms hold for it. That seems like it's kind of a drag. I mean, that's a lot of things to check, right? So one of the reasons I go over this list of examples is you can say, it was an example we covered, right? So I know it's a vector space. Like we said, this was a vector space in class. I have not actually gone through all of the details, but enough, I hope that you can see these things are true. By the way, this example has many, 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 many things hidden in it, right? See, because S could be a vector space. So functions from a vector space to a vector space themselves form a vector space, the set of functions on a vector space. If this W is real, this could also be real. Real valued functions of real variable form a vector space. Complex valued functions of a real variable form a vector space. Matrix valued functions of a real variable form a vector space. This example 8 is very meta. I mean, there's hundreds, millions really, of examples in there. Another example I have in the notes is polynomials, right? You could think about polynomials as functions, or you could think of them as sort of abstract objects. If you have two polynomials, right, which is a sum of finitely many powers of x multiplied by numbers, right? If you take that and add it to another such thing, you get another polynomial, right? If you take the scalar multiple of a polynomial, you get a polynomial. So the set of polynomials also forms a vector space. And you could take the coefficients of the polynomial to be real numbers or other things. So that's another example we'll come back to. All right, so there's our basic set of examples. I have a few less basic ones in the notes. Let me write for you our first theorem of linear algebra. Since I'm not actually going to prove these today, I'll erase these. No! I'm probably going to regret this, but oh well. So these theorems I tend to use without reference going forward because they're just so basic. But the proofs are in the notes. So F a field, V a vector space over the field with 0 in V, all right? And C is a scalar. By the way, things in here, they're called scalars. Things in V, vectors. You're like, does that mean it's a function is a vector? Yes. Functions are vectors in proper context. Now, if I want to emphasize that, I will say something like they're abstract vectors. Right? The vectors we've been studying up till now have been concrete vectors. Or sometimes I'll call them column vectors to emphasize. Of course, we've also studied row vectors, right? But number 1, 0 times x is equal to 0. Number 2, C, scalar multiplied by the 0 vector, is guess what? The 0 vector. 3, minus 1, scalar multiplied by x is equal to the additive inverse of x. And 4, if, there's a dot missing here. C dot x is equal to 0, then C equals to 0 or x equals to 0. Now the first, this is for all x, of course. This is for all C. And this is for all x. There's also a law of cancellation, which is that says the following: if a, x, and y are in the vector space V, right? Let's say, suppose a, x, and y are vectors in a vector space, all right? Period. If x plus a is equal to y plus a, then x equals to y.
What is that first symbol at the beginning of that?
Oh, suppose. There you go. That's why you shouldn't use shorthand. All right. Now, I have careful, gory proofs of this that proceed axiom by axiom application. Like we apply one axiom after the other to systematically prove these 4 things. All right? And if you're a math major, it will make you giddy. I mean, you might actually enjoy this. I sometimes enjoy this, but I don't enjoy it when I'm crunched for time, which is right now. So I'll let you read those. And if you ask nicely, I'll actually go through one of them tomorrow in the help session. When I ask a question about the proofs of these on an exam, like say test 2, if I do that, I state the definition in its entirety so you can refer to the axioms by their numbers. See, because unless I do that, it's impossible to grade because they're picky, you know? And I have done that in the past, but not like the last year or the year before that. But we're kind of about due for that. I don't know. So I do want you to study the proofs of these, all right? So I will actually work through one of them in the help session tomorrow. But what I'm really excited about telling you is the next thing, which is the subspace theorem. And here, you start to really see where a lot of your homework is coming from. A lot of the homework is about this. So section 6.2, and this is really how we build more interesting things, subspaces. So what's a subspace? Definition, let V be a vector space over F, all right? If W is a subset of V such that W is a vector space with respect to the operations of V restricted to W. All right. Then we say W is a subspace of V and write W less than or equal to V. So let's be picky. Subspace. This just says subset. Okay? Two stupid examples. Right? The one would be, how about the set just containing 0? That's a subspace of V, right? Check it out. Imagine all of the things I just erased. 0 plus 0 is 0. Scalar multiple of 0, 0. Additive inverse of 0, 0. Go down the list. You got all your axioms. Trivially satisfied. Pun intended. So yes, the set just containing 0 is in fact a subspace. It's the trivial subspace. What's the other stupid example? Can you tell me? What's that? What? The space itself, right. V is a subspace of V. Because, of course, V is a vector space with respect to the operations of V. Now, what are you actually in? What kind of subspaces are we most interested in? Is non-trivial proper subspaces, right? So a proper subspace, if we have W is less than or equal to V with, W not equal to V, then W is a proper subspace, is a proper subspace. For example, 0 is a proper subspace, but not a terribly interesting one. All right? So what are examples of subspaces? Well, there's tons of them. I have a few examples right in here. But I'm going to go ahead and state the subspace test theorem for you, because it really should be stated on the same day we've gone over the axiom, because the proof of the subspace test theorem really is nothing more than just reading through the axioms and seeing, oh, they just restrict naturally. And the subspace test theorem is the following. Here it is. Let V be vector space over the field F with, and suppose W is a subset of V with W not equal to the empty set. Then W is a subspace of V if and only if the following two conditions hold true. One, if x and y are in W, then x plus y is in W. And two, if x is in W and C is in the field, then C dot x is in W. Right? In words, what am I saying? Condition 1 says that, condition 1 simply says that W is closed under addition, right? And condition 2 says it's closed under scalar multiplication. Right? Now think about this. So if W is a subspace, right? Then what? Then it's a vector space with respect to the operations of V. So clearly, it's closed under addition and scalar multiplication. So 1 and 2 definitely follow. How about the converse direction? Suppose 1 and 2 are true for a non-empty subset of a vector space V, right? So we've already got the closure of addition and scalar multiplication for the operations restricted to W. We're assuming that. So we need the rest of the axioms, right? Commutativity, associativity, existence of inverse, all these things, right? And if you go down the list, they follow immediately from the data. Like, for example, here's a, I mean, you know, for example, if I have X and Y are in W, right? Then consider X plus Y, right? Well, that's equal to Y plus X, since X comma Y are also where? W is a subset of V, right? So if X and Y are in W, they're also in V. And if they're in V, and V is a vector space, that means the addition's commutative. So the subspace inherits all of those axioms in the same way. All right, so that's the subspace test theorem. So this is actually really nice because what it means is that we don't have to check all the axioms to prove a subset is actually a vector space, right? We just have to identify it as living in the, the shadow of some legitimate vector space and check closure under addition and scalar multiplication. I'll show you an example. How about this? Let's say W is A in R n by n, such that A transpose equals to A. This is what? Well, some of you know. The set of symmetric matrices, right? Clearly a subset of n by n real matrices, which we've just discussed, form a vector space, right? So is 0 in W? Well, 0 transpose is equal to 0, right? So therefore 0 is in W, which we can conclude is non-empty. Okay, it's non-empty. If we have A and B in W, then what's A plus B transpose? We worked it out. Properties of transpose. That's A transpose plus B transpose, right? But we assumed that A and B are in W, which means what? A transpose A and B transpose is B. Hey, check it out. A plus B just met the condition to get into the symmetric matrix club. What's the condition? What's the door charge? The door charge is that you must be equal to your transpose. If you have met that condition, you're one of the cool people. We let you in. So there you go. A plus B. Not that I really know much about these sorts of things, but anyway, A plus B, not really part of my life experience so much, but A plus B is an element of W. So we have closure under addition. Scalar multiplication, well, what's C A transpose? It's C times A transpose, which is C times A. So CA is an element of W. Therefore, by the subspace test theorem, the set of symmetric real matrices forms a vector space. In fact, a subspace of Rn by n. Almost the same example, almost the same calculation will show you the subset, the set of antisymmetric matrices forms a subspace, right? And there's so much more. But anyway, that's enough for today. Let me give you back your test.